Hi, my name is Jonathan Pickworth. Welcome to this webinar. I will be presenting today how non-contact measuring techniques can be used to replace traditional sensors. I have with me my colleague Charles, who is an expert in mechanical testing. He will show real-life applications directly in our software. So let's get started. Our customers point out some common issues in mechanical testing. Strain gauges, LVDTs, and accelerometers are so painful to install. It's really hard to predict where to install my sensors. I need to validate my FEA, but I don't have enough data points. I need more data points, but it takes so long to set up. Well, our ARAMIS sensors have been designed to solve these problems. So this is an ARAMIS system. It is composed of a pair of cameras, left and right, and a light. They are non-contact, meaning they can measure without contact strains and displacements. They are full field, meaning they can measure on the whole surface of the object. They can measure displacement and strain at the same time. They can be used for micro scale up to very large scale, just by changing the lenses. They can be used for static, all the way to very high-speed tests using high-speed cameras, and can be used for validating simulation and for model analysis. So this is an example of an ARAMIS data created here on this composite coupon. And what we see here is a full field strain map. And we placed a couple points here to measure locally, like a strain gauge, what would be the strain at this location. So here is a kind of a panel of different applications of the ARAMIS system, from material characterization to component testing or crash testing. We're going to focus on several of these applications in a minute. But how does it work? So we use a stereoscopic measurement system, a pair of cameras. And just like your eyes can see 3D, the software ARAMIS acts like the brain and gets the left and the right images together into a 3D mesh. Two techniques are used. First, using marker identification, the software is capable of doing point tracking. And so that's very useful for trajectory analysis or displacement measurements, acceleration, or 6 degrees of freedom. If you apply a speckle pattern on the specimen, the strain map can be measured on the whole surface of the object. Basically, each of these little speckles becomes a data point, and you can measure the whole object. Let's take a look at the product development cycle. First, we need to pick a material. In order to pick a material, we need to do testing to measure the material properties. We'll focus in our first part in how to use non-contact measuring techniques to calculate material properties. Then when we picked the material, we are producing the design, creating a prototype, and then testing this prototype. In our second part, we'll take a look at some testing done on components in different industries. I've got a couple applications that I will show, and then my colleague Charles will present an actual demo on real data. Then most of the times, in order to build confidence in the simulation, we need to perform simulation validation. And our systems are designed to be able to do that very easily. We'll show that in our third part. So let's start with material properties. Non-contact measuring systems can provide automated material characterization in 3 typical cases: tensile testing, bulge testing, and for forming limit analysis. In tensile tests, the ARAMIS system can be attached to a load frame like a MTS or Instron frame to be used as a video extensometer. But it can provide much more data. As you can see in this video, we can see on the surface of the object the ludus bands, we can see the load fronts, but also possible negative effect of clamping. And if we connect the load frame on the other end to provide the load to the ARAMIS system, ARAMIS will be able to calculate automatically the stress-strain curve, but also material properties according to standards from ISO or ASTM. Now let's take a look at a live demonstration. My colleague Charles will demonstrate how to use our software to measure the strain map on a tensile test coupon and automatically calculate the material properties.
Thank you, Jonathan. All right, since we're talking about automations of materials, let's go ahead and look at this ARAMIS project where we have a plastic specimen being loaded in tension until failure. If I look at the timeline in the bottom here, you can see going from the very beginning of the test into the elastic and then following into the plastic region of this test all the way to necking and failure of the coupon. Now, if I turn off the actual image here, we can also look at the mesh, which is the DIC, the digital image correlation map, computed from the pixels in the images. Now this mesh, if I play again the whole test, you will see it moves, expands, and strains, and this is the basis for our calculations. Now, computing the material properties, as we just said, is really easy in ARAMIS. I'll simply right-click to start by preparing my specimen. This will realign my project, so even if my sensor was misaligned, it will define the y-axis based on the original position of the specimen against its longitudinal axis. Now, the next thing we'll do is evaluate, so compute the data on that mesh, so for every single nodes. And this was a 1/4 inch specimen, 1.23 millimeter thick. And these are about 200 by 2500s to define our elastic region. Let's actually skip it, and we have different standards here that we can use. I'm just going to compute manually the modulus and the Poissons, and I'm going to skip the NR and the other values here, which wouldn't make all too much sense. All right, I'll go ahead and compute this, and this will launch the computations of the strain maps as well as the automatic definition of the best fit modulus curves and Poisson's curves using all of our pictures in this test. Again, that's a total of 150 pictures and total of 500 nodes across the entire surface. Okay, so we start seeing some of those mapping showing up on the screen, and you can see on the left the software is computing a lot of data. At the same time, it's actually preparing what we call report pages, which are going to be pages in a PDF, which we can export quickly to document and archive the data for every coupon we do if we have a large number of them to do. In this case, that's it. We have our final map shown up on the screen, as well as the Poisson and modulus value for the specimen. And if we look again to the entire play, we can see the strains really loading up in the center area where the necking really appears. All right, so that's it, just showing up quickly how we can compute the material properties of a tensile specimen within just a few clicks. All right, so that's it for the automatic calculations of the material properties on a tensile test specimen. This is obviously not the only automations that we can do, but let me now turn it back to you, Jonathan.
Thanks, Charles. So now let's take a look at how ARAMIS can be used on a sheet metal testing press to measure material properties specific to sheet metal. It can be used to measure the forming limit curve following an Nakashima or Marciniak test. It can also be used on a bulge test to measure the biaxial yield curve. So going back to our product development cycle here, now let's dive in to the prototype or component testing. Let's take a look at some industries where ARAMIS is used to measure strains and displacement. In the automotive industry, it is used a lot for crash and safety testing, aerodynamics, environmental testing, and stiffness analysis. In the aerospace, a lot of structural and fatigue testing is done, as well as vibration testing, impact, or aerodynamics as well. In biomechanics, a lot of tests is done in implant research to measure micromotion, for example, between the bone and the implant, also for prosthetic or orthopedics, and for motion analysis. In civil engineering, it is used to monitor and analyze the damage. It can be used to measure the crack propagation in concrete, in buildings, etc. For consumer goods, like phones or shoes, it can be used for drop testing, motion analysis, fatigue, etc. Let's take a look at this application in the automotive industry. So we have a Formula One car here that is in a wind tunnel on a flat track, and we are interested in measuring the 3D coordinates of the bumper in the coordinate system of the front cover or the main body of the car. So here we have placed target dots on the bumper as well as the car, and we're using a rigid body motion compensation from the front cover of the car, so we can isolate the motion of the bumper to be in the coordinate system of the car itself. So here we're looking at a sweep, so we are increasing slowly the speed of the car, and we're measuring the displacement here of the bumper. Then we perform tests at different speeds at steady state, so we can have a better understanding of the displacement of the bumper at each stage. In this application, we're going to be looking at a full-size aircraft crash test. For customers at the NASA Langley crash test facility, they do really cool things. They crash full-size aircraft. And so you see on this picture here, this is a former astronaut training facility back from the Apollo program, where they used to train Neil Armstrong and the other astronauts to land the module on the moon. And now our customer Justin Little at NASA is using this facility to crash tests. So you can see on the photo we have a big pool that's used for water landing, and also different types of ground on the floor for earth landing. So the goal here is to measure or to establish a study on the safety features, avionic, also looking at the aerostructures, how they resist during crash tests. And they put crash test dummies inside the planes to see how they survive different conditions of crash. So this is an example here. This is a Cessna 172 that is crashed on a more rough ground here. And we are measuring the major strain on the surface of the plane during the crash. This test was performed mainly to identify how the beacons that go off during a crash would react to a crash itself. And that data was kind of a bonus here to show the strains on the surface. This test is also very interesting. So this is a Chinook helicopter crashing, and we're looking at the buckling. This is the out-of-plane displacement that is measured. A couple things that we can notice on this video that are really interesting to see. In the background, you see this grid here, and that's actually the largest calibration panel in the world for optical metrology systems. They use this wall that used to be a training wall for astronauts to learn how to walk on the moon. Since the wall is tilted 13 degrees, now has been reconverted into a calibration object. And you can see those target dots, little smiley face target dots, and these are coded markers that are used to calibrate our sensor. The other thing that we can notice that's interesting is the size of the speckled pattern on the surface of the object. In this case, we have such a large field of view that the speckled pattern cannot be applied with spray paint, or stamps. These were individually marked dots on the surface of the object. The next application is in civil engineering. In civil engineering, it's very important to understand how cracks work. So this is an example of a concrete beam that's a reinforced concrete that's placed on a 3-point bend test. And we're trying to look at the strains and the crack growth inside that middle section of the beam. So in this video, we're looking at the major strain, and so you see appearing the cracks even before they can be visible on the component. We can measure the strains appearing before. And then you see, of course, the beam breaks. But in this case, it is very difficult to identify beforehand where the crack is going to happen. So you cannot place a sensor to measure the crack growth beforehand. So with the ARAMIS system that is used here, we can record the images and then in post-processing go back in the data and place virtual sensors. So that's what has been done. And we see that we placed 3 little gauges in the field of view for measuring the crack 1, crack 2, and crack 3 growth. And still in civil engineering, this is a very interesting application here. It's a shaker table that is replicating earthquakes, and they placed here a brick wall. And so this video shows the results. On the left side, we've got the displacement during the loading, and on the right side, it's a scale of strain showing in red the high strains that are showing basically the cracks. So you can see the effects on both sides here, displacements and strains, showing that the crack growth appearing. So now let's move on to a live demonstration. My colleague Charles will show how to go back in the data and inspect this optical measurement data in order to get strain, virtual strain data.
All right, thank you very much once again, Jonathan. And let me now talk about the virtual strain gauge positioning. So one of the great things about the DIC data is since we have a full field data set, we don't need to know beforehand where exactly should we put our strain gauge. And we don't need to mark the exact position of that strain gauge. We can simply use the CAD file to find the exact coordinate location of a point and define a strain gauge at that location. We can also do the other way around and end up at the end of the test seeing a maximum strain in a specific locations, defining a strain gauge there, a virtual gauge, and then locating that in the CAD coordinate system to know exactly where it was at the very beginning of the test. So let's look at those two things separately, and that will encompass the live demo about virtual strain gauge. The first thing here is we are seeing the same component that we talked about a few minutes ago in the tomography example, where we have a component that's being loaded from the top here and basically being bended. So if I go to the timeline here, you see it's being bended a little bit and then released, and going again for a second cycle, bended and released. We have the image mapping here, but also once again the actual mesh from the DIC data, and we're seeing that mesh move in 3D space in time. Now, what I've already did before doing that demo is I've imported the CAD file, so we can see here the actual part in 3D space. And this part also comes in with its own coordinate system, which is at the very bottom of that part, with Y, X, and Z being defined from the CAD file. Now, I mapped out and projected the exact location of the mesh from the ARAMIS data onto this CAD file. So now every node is being referenced with the CAD coordinate system, which is right here. Okay, so now that we have that, it means we can look at, and I'll hide again just the CAD for a second, and let's look at the actual major strain. So if I go into the project and start loading it up, you can see the strains going all the way up to almost 2% in that radii, and then continuing to release, and then once again. So the first things we could do is, like I said, let's go at one of the maximum stages and identify a location that we feel is the maximum load. And we want to know what is the location of that strain gauge. So let's create a virtual gauge. I'll right click to create a point. And I can identify maybe this location as well as this one right here. Oops, so we'll start with that one and another one right here. And maybe finally one that's in the middle of kind of nowhere, and finish that and close with those 3 points. So we have 3 gauges that I just created here, and I can really quickly, with a right click, define their positions and strains. So I'm gonna ask the software to compute the positions in X, Y, Z, again, in the CAD coordinate system, and the strains for every single value. So X, Y, major and minor strains, as well as even von Mises strains. And now if I look throughout the entire test, I do have the strains being computed for every single location and every single stage. And if I go all the way back to the beginning, you can see those points are tracked to their initial positions, and I can know exactly where the point 1, for example, is in X, Y, and Z. And I could compare, therefore, the values of my strains using my finite element model and using the exact same location from the CAD coordinate system. So that would be actually the second part. And then the other way would have been at the very beginning, we said, I know where to put my strain gauge to fit my maximum load in my finite element model. And I could have created the other way around. So I will create what we call a projection point. So I'll create the point at a specific location, and I'll try to find the closest point to that on my experimental data set. So projection point here, I can define my first point, and I will edit the location, edit the location, and say, let's try to go back to that exact same spot. So 132.10, 125.59, and minus 2.55. So I'm going for a very precise location in my CAD coordinates, and I'm going to project that point onto my DIC data. There's a really minimal distance deviation here, so I found within 2 microns a location on that surface. Okay, so now I have my point 4 that's on my mesh right here, and I can do the same thing and ask the position and strains across the entire project. So now obviously if I go throughout the entire project, I will see the strains of point 4 at a specific time and space. All right. So that is it to demonstrate the possibility of creating strain gauge, virtual strain gauge at very precise locations without having to mark up and know before we start to test where that gauge is in space. We can either mark it using the CAD coordinates or simply create it at the very maximum level and get back to tracking where was that position at the very beginning of the test. All right, that's it for me on virtual strain gauge positioning. And now back to you, Jonathan.
Thanks, Charles. So now let's move on to the third part of our presentation on simulation validation. The ARAMIS system is designed to measure the shape, the displacement, and the strain full field. So nowadays, it's used more and more in the industry to validate FEA models, build confidence in them by providing much more data than standard strain gauges or extensometers. Let's move on to another live demonstration to show actually how it works in the software.
All right, thanks again, Jonathan. So for this demonstration, I want to talk about the FEA comparison, and the example I have in front of me here is a loading on a wrench. So this is a very simple project, only just 6 stages, and we're going to compare those 6 stages to an FEA model result. You can see here, we're looking at the principal strain mapping. If we get rid of the images, we're going to see that we have a very good definition of the strain pattern throughout the entire surface, as this was captured with our latest SRX ARAMIS system with 12 megapixel resolution. So we have very small strain patterns showing up here throughout the entire bolt. Our very first step is to align the projects with the CAD model. So if we look at the coordinate system right now, it's quite arbitrary right here in the middle of the measurement. I am gonna import our FEA model. So FEA import. And the first thing I'm gonna pick is the reference file. So when there's no loading, and I'm gonna use that to align the two projects together. This is very important step, a very, very important step, as it's vital to align the mesh from the experiment and the mesh from the FEA analysis. So I'm gonna open up the picture-in-picture here with only the CAD file in it shown exclusively at the top. And my 3D view here, I'm simply gonna show the actual wrench. So this here is our actual mesh, and this in the dark blue is the FEA mesh. I'm gonna hide the epsilon 1 mesh and simply look at the two different elements. I'm gonna do a simple alignment here. We have a lot of different alignments possible in software, but the first one I'm gonna use is a 3-point alignment, simply matching up a point in the CAD file with a point in the actual mesh, doing that 3 times to lock the 6 degrees of freedom in our part. So here it goes, picking up a nominal point right here at the tip of that wrench and identifying where that is in the actual mesh. Doing that again at the very center of the wrench, and that is right here. And finally at the tip of the bottom fork of the wrench, and that is right here. All right, so automatically you can see that I'm now using actually the CAD coordinates. I'll just validate that and we can have a look at the CAD. I'll hide the picture-in-picture now. And if we turn on the CAD file with the mesh, you can see they're very well superposed next to each other right now. And I am using the CAD coordinate that are coming from the FEA analysis. So if I were to look at a specific orientations of strains, I would have them in the same orientation as the CAD file. So you can see here axis along the line of that element. Okay, to do a comparison from a DIC analysis to an FEA analysis, the first thing we need to do is inspect both meshes to see the major strain, 1 from the DIC data and 2 from the FEA data. So I will go ahead and inspect those 2 elements. To do that, right now I only have a fixed element, so if I look at every stages, the CAD file is not moving, and that's normal. I want to import now the deformed mesh for every single loading in that project. So I will hide this undeforming CAD element, and I will now import again my FEA, but this time not a fixed rigid CAD, but a surface component, so a surface that's deforming stage by stage. So I'll go ahead and select the stages that I've already created and populated from my FEA software, in this case for my ANSYS analysis, and stage by stage I will import that mesh. Now, I have a mesh. If I go from 1 to 6, you can really see that the 2 meshes are deforming, both from the actual element and the other one from the FEA, and by that they are kind of turning on and off. To do a comparison, I will inspect those 2 elements, which I can see here, in my 3. I have the FEA component and the wrench, and I will inspect those 2 meshes to look at their principal strains. So if I start with the FEA component, I want to inspect it for the major strain along the entire mesh. Okay, so for technical strains now, I can look at the mesh changing here, and using my legend, I can see, the areas that are being subjected to more strains all around my component. I'll do the same thing for the wrench, for the major strains. Okay. And again, I'm bringing back those strains that we were seeing at the very beginning of this short demonstration, and I have the strain pattern all around the entire surface. The next thing would be one. I'm gonna hide the local one. The first thing is to put the FEA result on the actual mesh, right? So we only have one mesh that can be a master here, and we're going to use our actual DIC representation from the experiment. So I'm going to put the data from every single node on our FEA mesh and project it onto that surface, which is our actual mesh. Once we have that, we will be able to compare the difference between the two different results on every single node. So on my wrench, I will now inspect the map of my actual data on the mesh. So map on actual mesh. And I'm simply going to pick here, I want to project the FEA result, the major strain, onto my mesh. Okay. You can see here it already pretty much matches up very effectively with the FEA mesh. But what I'm getting now is for every node of my actual result, the value for that node based off of the finite element. And I am getting that in the ARAMIS software for every single stages. So if I'm hiding entirely, and we will do that now, if I'm hiding entirely the FEA component, and I'm only looking at the projection of those points onto my mesh. So if I don't have a node which is measured by the DIC system, I will not project the data from the FEA onto that experimental mesh. Okay, so this is really just the results from the FEA mapped onto our actual mesh. And the next step is simply to compare the data between the two. So I will do the strain comparison between my FEA data, which is what I just projected, the FEA data on my actual mesh, from the DIC data, which is going to be down here, the wrench.epsilon1. All right. And this will instantly give me across the entire field of view for this mesh a comparison between the actual data and the FEA data for every single loading conditions. Okay, and that's it, as simple as that. In a few steps, we brought in the CAD file, which we used to align our data sets, so we had coordinate systems that would match up between the FEA data and the ARAMIS data. Then we imported the deformed mesh for every single stage. Okay, which we can see here. On that deformed mesh, we inspected the major strain, and then we projected those major strains on our actual mesh to finally compare the difference between the two meshes. And now for the entire surface here, and just to compare, to have a look here, we have a total of 9,700 data points, 9,700 nodes, which we're comparing the data from the FEA model down to the experimental ARAMIS data set. And we're getting the full field difference between those two analyses. So we can easily predict where is the model not giving us the right results, and how can we change and improve our model to have it validate the experimental data. So that's it for me, just showing up a quick comparison between an FEA data set and an experimental data set, and mapping out the difference between those two. Back to you, Jonathan.
Thanks again, Charles. Coming back on the product development cycle, we have shown that The ARAMIS system can be used for material characterization, for testing components and prototypes, but also to validate simulation. As a conclusion, I wanted to point out the benefits of optical metrology. First, flexibility. With the same sensor in the same test, you can measure strains, displacements, acceleration, and much more at the same time. It's also very easy to use. For repetitive tests, you don't have to put a strain gauge or a sensor again and again on each specimen. You can have then faster cycles. You also get live feedback of the strains or whatever inspection you asked ARAMIS to show. You have a live feedback of this inspection on the screen while the test is performed. And finally, you have a lot of additional capabilities. It can be integrated to the testing environment, connected to the load frames, for example. We can do complex triggering, so that can be used for example, fatigue testing or complex testing. We also have a lot of automation capabilities to calculate material properties or to automate processing. It can be used for dynamic testing using high-speed cameras, also for vibration testing, FEA validation. We can also import thermal images. As a bonus here, I wanted to show that today you could actually start using this technology directly in your lab. We offer GOM Correlate, which is a free software for 2D DIC endpoint tracking. So you can go to www.gom-correlate.com and download GOM Correlate. That will allow you to use any camera and do DIC or point tracking in 2D, meaning you don't have the third dimension. So this is the limitation here for the free software. But you could start using that technology right now. This website has a lot of content as well to learn this software. We also offer GOM Snap 2D, which is an acquisition software that you can use with any generic USB 3 cameras. So feel free to download that as well and start using DIC and point tracking right away. And finally, for universities, we offer a free teaching package that includes the software GOM Correlate and also lab classes, class notes for the teacher to implement a full course on optical metrology for undergrad and graduate students. So I wanted to finish this presentation by a quote from one of our customers at Boeing. So we asked him, you originally purchased the ARAMIS system for composite buckling study. What are you using the system now? And his answer was everything. And that was one of the best compliments we received at Trilion. Thank you so much for your attention.